Hi friends, welcome to Civil Architecture Tutorials channel. Today we discuss regarding the beam design details. So let us go to the A-frame. That is a beam and two columns. Okay, you can see this two columns and beams. So what is the clear span and what is the effective span in this beam? That first we will look into. The clear span is the space between two columns. Okay, this column and this column, the whatever be the space in between these two columns is called the clear span. So here it is 3.7 meter. Suppose it is 3.7 meter. And then what is the effective span? Effective span starts from the center of the column, from one center of the column to the other column center, like this column center starts from here to the second column center is effective span, and it comes to 4 meter. So the effective span is 4 meter here and the clear span is 3.7 meter. How it comes? Because the beam here is, beam size is 250 mm into 300 mm and the column size is 300 mm into 300 mm. So if it is 3.7 mm is the clear span, and this is how much? This is 300 mm and this is 300 mm. So 300 mm by 2 is 150 mm. Here is all 150 mm. So 150 plus 150 is total around is 300 mm. So 3.7 plus 300 or 3.7 plus 0.3 is equal to 4 meter. That is the effective span. That's by that we can come to the effective span. If we know the clear span and the width of this column, these two columns, then we can get the effective span of that beam. Okay, the beam, the columns on which the beam is resting. So we got, I think now you understand what is clear span and what is effective span. This span we will get by adding the half of the two columns on which the beam is resting plus the clear span. So we got 4 meter. I think you understand this thing. And then suppose a uniformly distributed load is acting on this beam, like this. Uniformly distributed load is acting on this beam. So when a uniformly distributed load is acting on a beam, what will happen? There will be a bending moment. So now we will see the bending moment diagram, how this bending moment is acting or how the bending moment looks. And this is the bending moment. When the uniform distributed UDL is acting on here, the bending moment will take a shape like this. See, at the center of the beam it will be sagging, and on both sides where the column is there it will be hogging. That is, at the center it will be positive bending moment, and at these two sides, that is this side and this side, it will be negative bending moment, or it is shear force acting on those two sides. Okay, these two sides there will be shear force, and this is positive bending moment, and this is so in this area, this area, this area, in these three areas there will be bending moment. So that means we need to give some strength, we need to add more steel into these three areas only. That is this area, this area, this area. Okay, we need to make the framework of the beam. To make the framework of the beam, we need to give at least 4 reinforcement bars. Okay, so that is, first one is the top reinforcement bar, that is this, and second is bottom reinforcement bar, that is top main bar and bottom main bar. These are the main bars on which the beam is making its shape, or the framework of the beam. So top main bar like this and the bottom main bar like this. So how can we know the length of this top main bar? Let us take the case of top main bar only. Top main bar means, if we are taking this length, this is the top main bar. Top main bar is this. So we know the clear span, that is 3.7. 3.7 is from here to here, that is 3.7 meter, which is the distance between here to here. So that much length of the top main bar we know, and then the rest what we don't know is the length from here to here and here to here. So how we know that length? That length is actually called the anchorage length or development length, or LD. So LD is actually, it is 50D for the beam, where D is the diameter of the bar. Okay, so this much we know, 3.7 meter, and this much we need to know, which is 50D. So that is 50 into, if the dia of the bar is 12 mm, 50 into 12, okay, that is 600 mm. Okay, so this much we know 3.7 meter, and this is 15 d 600 mm or 0.6. So how much will be the total from here to here? 3.7 plus 0.6 or 3700 from here to here plus 600 mm, and this element length 600 mm will give us 4900 mm or 4.9 meter. That is the total length of the top main bar. And why this anchorage length is given is that we need to have some anchorage for the beam into the column, otherwise the beam will slip. And also to transfer the force from the beam to the column, this anchorage diagonal length is a necessity, and the formula is 50d. So now we got the total length of the top main bar from here to here. The same we have to give the take the measurement of the bottom main bar. It is the same, that is this bottom main bar, unless the diameter of that bottom main bar is different. If it is 12 mm, then it will be the same 4.9 meter or 4900 millimeter. If the diameter of the bottom bar is different, usually it is different because, as you know, in a beam, the tensile area is at the downside where the moment is acting, so we need to add more steel. Sometimes they are provide a bigger dia of steel also is given at this same. So then you have to 50 into d means d will be maybe 16, 15 into d, because that much difference will be there in the length of that bottom main bar. Okay, so we know this top main bar and bottom main bar. There will be at least 4 main bars in a beam, 2 top main bar and 2 bottom main bar. It would be more, but at least minimum should be 4 main bars. So now we know the length of top main bar and bottom main bar. And now, before I said that there will be bending moment acting like this, so we need to add more steel into the positive bending moment and also negative bending moment area. Okay, so this is the bending moment diagram which I explained before. Now we will go into the bending moment which acts on this beam. We will put that diagram into this beam. It's like this. This is a uniform distributed load. UDL is acting on the top, and how the bending moment is acting like this. Here the shear force will be high here. Here also it is high, and the bending moment is positive in the middle. And that's why we provide more steel in this area, this area, this area. There is a point in which this bending moment is transferred to the negative shear force. Okay, or bending moment is transferred to shear force here, or positive to negative. There's a point in all the beam. There are 2 points, 1, 2. So in this point the shear force will be 0. There is no force acting on that particular point only. So that points are called point of contraflexures. So again I am telling, point of contraflexures are the points in a beam at which point the positive bending moment is transferring to negative bending moment or shear force. So at that point the force is 0. So this is the point of contraflexure, and point of contraflexure is it is L by 4 at a distance of L by 4, where L is the effective length, effective span of this beam. Okay, L by 4, L by 4. So now we will see the length of top extra bar, because like I said, since there is a negative bending moment here, we need to provide top extra bar here, top extra bar here also, like this, top extra bar here, top extra bar here. So we will calculate the length of that top extra bar now. Here also the anchorage is same, that is, if it is D is 12, 12 into 60, so that we know the cutting length of that is 600 mm. So this part is same, 50D. Okay, 50 into D, diamond length at this particular area, plus we need to know from this point to this point, and which is L by 4. L is the free length, that is L is 4 meter, 4 meter by 4, 4 by 4 is equal to 1. So that is the length of the top extra bar is 600. This area 600 plus 1000 is 1700 mm or 1.6 meter. The same is here also, 1.6 or 1600 millimeter. Now we need to know the length of this bottom bar, because we need to give more steel at the area where the positive bending moment is acting. So how to know how to get the length of this bottom extra bar? Bottom extra bar, there is another formula called 0.15 L. 0.15 L means L is, like I said, the FT span. So 0.15 into 4 meter is equal to 600 mm again, 600 mm here and here. 0.15 L from here and here we have to decrease from the total clear span. Now we have to deal with the distance between these two columns only. So that is clear span. Clear span minus L by 4, L by 4. Okay, that will be 3.7 meter. 3.7 meter minus, or 3700 minus 600. What is 600? 0.15 L. L is FT length. So 3700 minus 600 minus 600. So we had to reduce 2 L by 4 from here, and to get this length of this bottom extra bar, which comes to 2500 mm or 2.5 meter. So now we know the length of the top main bar, bottom main bar, top extra bars and bottom extra bar. That means we did the bar bending schedule of a beam in general. Okay, and here it is curtailed. The steels are cutting are in different positions. It doesn't connect each other. Okay, but we can also see, we used to see crank bars where the same steel is going into a crank, and then the same top bar is going to the bottom bar, and then again it comes to the top bar, which is like the crank bar system, like here. Okay, but the problem is that the length of this crank area is 1.42 H. This happens at the point of contact pressure where there is no force is acting. So that means in that particular steel is not taking any load, because it is going through the zero force. So the length of that bar is 1.4 H, which is actually a waste. We don't, if we want to reduce the length of the steel, then we don't have to go for crank bars. Instead, it's always better to go for this curtailment bar like this. Provide separate bar here and bar separate here too, and which also for workmanship also, this is far better than going for crank steel. This is the benefit of going for these curtailment bars. So I think now you understand the beam steel details or BBS of a beam. So I will come with a new subject in a new video. Till then, goodbye. Please subscribe, share and like my channel. Thank you very much.